Okay. So today we're going to talk about function operations and factoring. So function operations include things like adding things together, multiplying things. We're not going to divide because division is surprisingly quite complicated. Subtracting, a little bit complicated. So the first thing is just some vocabulary. So an algebraic expression, these are formed using constants, variables, and the operations of addition, subtraction, multiplication, division, raising to powers, taking roots. Notice that stuff that's not included are like taking like the sine or cosine of something. Have you guys heard of sine and cosine before? Or natural logs, not included, okay? So algebraic stuff is just addition, subtraction, multiplication, division, powers, and roots. So examples would be stuff like the cube root of x squared plus 5. Something like that. 5x squared minus 7x plus pi, because why not add an irrational number? Or something like x squared minus 1 over 2x plus 3. Those are all algebraic expressions. Something that's not would be like ln of x plus 10. That's not an algebraic expression. That's something different. Okay, and then it's kind of like there are rectangles and squares or special rectangles. There are special kinds of algebraic expressions, and they're called polynomials. And polynomials are expressions that involve only addition, subtraction, multiplication, and raising to a natural number power. So what were the natural numbers again? 1, 2, 3. So your powers have to be positive whole numbers. Does that make sense? So polynomials, oh, I love alliteration. Do you guys know what alliteration is? Yeah, like using the same letter. Polynomials are positive powers. Okay, I try so hard. Okay, polynomial positive power. Woo, go Power Rangers. You can tell I grew up in the 80s. Okay, so some examples of polynomials are stuff like, you guys are a tough crowd, 2x minus 3. If I start making Doctor Who jokes, will you laugh? Anybody else a Whovian besides me? Oh, I love Doctor Who. It's a problem. I'm seeing therapy for it. So.
Why? Anyone even the slightest bit interesting is mad in some way or another.
I'm totally mad. Okay, I'm definitely a madman with a box. Okay, so there are polynomials. And also, polynomials can have more than one variable, but in calculus, you're almost always only going to see them with one variable. But just, like, technically speaking, something like x minus 2y is a polynomial. Something like x cubed minus 3x squared y plus xy squared is also a polynomial. So they technically count, but you don't see them quite as often in calculus. I think you'll see them more often in calculus 3 has stuff that has more than one variable. You start to graph stuff as like three-dimensional. It's all weird and stuff. So calc 3. Okay, now polynomials. So in a polynomial, a variable cannot appear in a denominator. I'm just going to abbreviate that because spelling is hard. An exponent or within a radical. And then a polynomial in one variable is constructed by adding stuff in the form of this, which is just saying like adding stuff where you have numbers times something to a power. The powers have to be whole numbers, but the numbers in front of the powers could be irrational things. Like, it's totally okay to have pi x to the 6th. Does that make sense? Okay, it's also okay to have square root of 2x to the 7th, right? That's also fine. The kicker is the power is the whole number thing. And the same thing is true when you have two variables. It's just that both the powers on the x and the y have to be whole numbers, but the number in front called the coefficient can be any kind of number at all, any real number. We're not going to have imaginary polynomials. So, and the degree of the polynomial is the highest, is the degree, or what I would say is the power of the non-zero term with the highest power. And that's easiest to explain with an example. So let's look at the next one. It says, which are polynomials, which are not, and if it is a polynomial, give its degree. So like this one, is this first one a polynomial? Yes. and its degree is equal to 2. It's the highest power. If the polynomial is written in what's called standard form, often the highest power is the power of the first thing, but polynomials are often written in reverse standard form where they go like constant down to the highest thing. So, how about the second one? Is that a polynomial? No. Next one? No. That's something called a rational function, which we'll discuss later in this class. Is this next one a polynomial? Yes. So the root 2 is just, there's no x there, right? You just added a number, that's okay. So what is the degree of that polynomial? 4. And in the terms of polynomials, the degree kind of like talks about the size of it, like how big it is. So bigger powers are kind of like bigger functions. And that will matter. Has anybody ever done division with polynomials? And the degree matters a lot. Yeah, and ordering them matters a lot too. We're probably going to discuss that in this class. If you've seen it, no problem. I haven't seen it either. Okay, add the following polynomials. So when you add polynomials, all you do is combine like terms, right? Yeah, okay, adding's easy. So I'm going to write down my steps, but go ahead and just see if you can add these and get the right thing. It's a quite a long answer. And I'll color code my work so it's easier for you to follow. Run out of colors. So great. Is it actually visible?
It was 90% right.
You're not, okay. I forgot the 7x, so I am not right. Thank you. I'm going to pretend that I made that mistake on purpose and I was testing you, and you passed. Good job. I forgot the 7x. So negative 5x plus 7x should have been plus how much x? 2x. I made my first major mistake this semester. That is one of many, so be careful. Some people make mistakes on purpose to test their students. I don't actually do that, but it ends up happening like inadvertently. So if something seems wrong, let me know. I'm not going to get mad at you. I'm going to get mad at me. Okay, great. Now subtraction is a bit more tricky. So the first tricky thing is figuring out what order this is. So it says subtract 4x squared minus 3x plus 5 from x squared minus 8. So who's first? X squared minus 8 is first. Does that make sense? Like I think about numbers, you know, take 2 from 7 is 7 minus 2, right? So this is x squared minus 8 minus 4x squared minus 3x plus 5. So that's tricky thing number 1. What is tricky thing number 2? Anybody know?
The middle term.
The negative does what? Distributes to everything. So this becomes, and that's really because this is a negative 1, and you sort of multiply it through. Does that make sense? Okay, so that's the same thing as x squared plus 8, or minus 8, had 2 mistakes in a row, minus 4x squared plus 3x minus 5, right? Just flip-flops all of a sudden. And then from there, just add like terms. Super easy. So negative 3x squared plus 3x. And then I think about minus 8 as in it's 8 below, feels like outside right now, and goes down 5. It got even colder, so it's negative how much now? 13. Great. Awesome. Part B is the exact same thing. How about you try it? I'll pause and drink coffee, and then I'll start. I don't know how fast I'm relative to you, but does that look like what you got? Okay.
Yep.
All right, great. So subtraction, not super hard. Now, this is the really hard thing about review stuff, is I don't think this book thought through it super thoroughly, because they had you multiply things with radicals before you multiplied polynomials, and polynomials are easier, right? So just think about this as distribution on steroids. Okay, so you just have to distribute everything, and you've got to be kind of systematic about it. And I think that the best method, after like years of teaching this, is to think you got the first thing in the first set of parentheses, distribute that. Does that make sense? And you've got the second thing in the first set of parentheses, then distribute that. The only thing to be a little bit careful about is that when you distribute the 3, the negative goes with it. Does that make sense? Okay, so first we get, so if I do 2x times 2x squared, what's that?
4x cubed.
Plus, next comes,
6x squared.
and then,
And 4.
great. And it's my own inability to plan, but I often run out of space, so I like write the next stuff on the next line. So next we do negative 3 times 2x squared. What does that make?
Negative 6x squared.
And I'm going to put it right here because then I can just add up and down, add vertically, right? Okay, and then minus 9x, and then lastly, plus or minus? Plus 6. And what happens when you have 6x squares and I take away your 6x squareds? You cry, because they're all gone. Yep, exactly. So 4x cubed minus 13x plus 6. Okay. Now, the next one, you've got to write a little small just to warn you. Okay. All right, so you guys have heard of PEMDAS, right? Like parentheses, exponents, then subtraction, right? So here's a common mistake, don't make it. That power of 2 doesn't distribute. So powers distribute over multiplication, meaning if I had like 2a times b, that power could distribute. But when it's over addition or subtraction, it doesn't work that way. And I can prove it to you if you just think back to what the basic definition of squared mean. Squared means base times itself, right? Does that make sense? So, for example, in this, 2a minus b squared, that means 2a minus b times 2a minus b, right? That's like the basic definition of what squared means, right? And then you've made that into a problem in which you can use distribution, right? Okay, so I also didn't do the second part yet, so I'm going to have minus a plus 2b times a plus 2b. So same thing. And I think, really, if you think about squared as, okay, squared means the base is twice, and always revert to that definition, you're probably almost never going to be wrong, barring like dumb errors. Does that also make sense? And the definition applies to cube. Like if you see cube, that means the base appears 3 times, right? That's 3. Okay, now multiply the 2a minus b times 2a minus b. So we get 4a squared, right? And then what comes next?
Minus 2a.
Minus 2a b. And then?
Minus 2ab.
Minus 2ab. And the order of the letters doesn't matter. I just choose to make them alphabetical. And then plus. Exactly. Great. Okay, now the next set, let's do the same thing. Minus. I'm going to make a slight mistake and then fix it. So a squared plus 2ab plus 2ab plus 4b squared. Is everyone okay with at least why this is what it is? Okay. Now, I made a slight mistake. Does anybody know what it was? I didn't distribute the negative, exactly. So what I'm going to do, because I haven't done that yet, is put parentheses here and here. Does that make sense? Okay. So now I'm going to do 2 things. I'm going to combine like terms, and I'm going to distribute the negative. So what's minus 2ab minus 2ab? Do they cancel? No. What do they become? Minus 4ab. So I've got 4a squared minus 4ab plus b squared minus the quantity. Oops, I said I was going to distribute, didn't I? Oh, I recorded that, and that's annoying. Okay, minus, that's a scribble, don't write that down, a squared. So when I add this 2ab plus 2ab, I get 4ab, right? Within the negative distribute, it's making it negative 4ab. Okay. And then minus 4b squared. Okay, so what's your final answer then? How many a squareds do you have?
3a squared.
Mm-hmm. And then minus how many ab's? 8. And then how many b squareds?
3.
Negative or positive?
Negative.
Negative. Okay. All right, so back in the day when you were in like elementary school, you probably, or even maybe algebra, you talked about how to factor numbers into products. Does that ring a bell? You've done that, you say, okay, well, 30 is a product of 2 times 3 times 5. So, and that product is specifically a product of primes, meaning that the 2, 3, and 5 are prime numbers, right? So we're going to do the same thing with polynomials, so, or algebraic expressions. So we're going to factor things like, we'll be given something like x squared plus 4, and the puzzle is like what 2 things multiplied together to make that, if anything, okay? Because polynomials can be prime, just like numbers can be prime. But figuring out how numbers are prime is actually quite tricky. You just know a few of them because you can like reason through them well, but like figuring out if a big number is prime is actually used in like developing like fancy unbreakable codes. So yeah, it's a common code making technique is using math and big prime numbers. So I don't know a lot about it, I just know that it occurs. So for example, this polynomial, x plus 2 is prime, because you can't write it as something times something else. But x squared minus 9 isn't, because x squared minus 9 equals x plus 3x minus 3. But these 2 things are prime, so that's completely factored. And you should have seen factoring in a previous class. Like, I know I taught it in Algebra 1 and Algebra 2, which you probably all had, right? Yeah. Okay. So the first thing is, if you are factoring, is this thing called taking out the greatest common factor, which is kind of like undoing distribution. So you look and see what is the biggest thing you can divide evenly into all 3 of those terms. So what's the number that can divide into all 3 of them? 3. And then x and y. Okay, and you think about, and the way you found the powers, you look at the powers and you pick the lowest such power and you compare them. Okay? And then you think, okay, well, if I divide out 3xy, 3 divided by 3 is 1, right? What's x squared, x, is the answer. What's x cubed divided by x? X squared. And then y divided by y is 1. So that's x, just x squared, I think. Minus. So what's 6 divided by 3? 2. X squared divided by x will be x, and then y. And the last term, what's that going to be? Minus y squared. And since this is the reversal process, this is like, this way is factoring, how could you check your answer?
You could distribute. You
could just multiply it back through, right? So one thing that will happen is if you haven't gotten everything in common out of it, it's not done. Does that make sense? Like, so if there should be no common sort of factors between the x squared, this, and that. So there's no x's in this term, right? So nothing in common. There's no y's in that term, nothing in common, right? There's no numbers that will, other than 1, that divide evenly into all those things. So, we're done. Now here's a weird one. Have you guys seen weird ones like this before? It's okay if you haven't. So, these both have, both this term and this term, what could you divide them both by evenly? 2y plus 5. That actually divides out. It's a little bit strange. But this becomes 2y plus 5. So that's been divided out. So what's left behind from the first term? 3y. And what's left behind from the second term, plus 2. So this is actually the common thing that undistributes and factors out. Is that a little mind-blowing? Let me explain that more, or are you okay with it? Yes?
The one that was before this, we used to pull out. Sorry, can I just see it?
Okay. Any additional questions about that one? Should we explain a little bit more, or do you think you get it? Okay. The next one, we're going to make it look like the previous one. And this is something called grouping, and some people teach, some people don't. But you try to look and see, do the first two terms have something in common that you can factor out, and do the last two terms have something in common? And right now, as is, they don't. You see how there's no commonality between the wy and the xz, right? And there's no commonality here either, right? But because these operations are commutative, you can move terms around. These two have an x in common, right? These two have what in common?
Y.
W and also 3, right? So I'm going to move this 3wz in front of the negative xz. So I'm going to rearrange the stuff like this. So I'm going to make it 6wy plus 3wz minus x. I'm going to do one more thing too. I guess that'll work. Let me think for a second. Sure, it'll work. Minus xz minus 2xy. And then you look at just these two together and just those two together and say, what do they have in common, just as groups? So, and the way you determine to make your groups is that somebody has something in common. Now, this isn't the only way to group stuff. You could have also put the 2xy with the 6wy. Okay, there's lots of ways to do this correctly. This isn't the only one. So what's the greatest common factor in the first set of two? 3w. And that will be, we're left behind with 2y plus z. Okay. Now the next two, it's actually good I did this way because it makes it a little bit trickier and it's good to explain what happens. They obviously have an x in common, right? What else do they have in common?
-1.
Negative, exactly. So let's take out negative x, which makes it z plus 2y. Is everyone okay with that? Okay, so the negative also undistributed. And now, is it or is it not just like the last one? Is this 2y plus z the same thing as z plus 2y? Yes. Technically, yes. You can take that out now. So you get 2y plus z times 3w minus x. And that's a technique called grouping. I think the name is pretty obvious why it's called grouping, right? You look at the terms in groups. And how you choose your groups is you just have to make sure that the groups have some kind of greatest common factor. Now, this step, going from here to here, depended upon this thing and that thing being the same thing. If they weren't the same thing, you can't do it. Does that make sense? Okay. Now, the most common factoring you see is stuff like this. You should be able to do this without having to think very much about it. So what I'm going to do with the very first example is actually multiply them together and look and see if we can figure out the pattern, because it's really easy. So multiply them together. There we go. Did everybody get x squared minus 4x minus 21? Okay, so now here's the puzzle. Pretend that you were given this, and someone's going to give you $100. You can figure out what was multiplied back together. Like what was it in the first place? You got to reason through like it's like a puzzle. Okay, what did that come from? So is it clear that because it was x squared, just regular x squared, it had to come from x times x, if we're looking at whole numbers only. Is that okay? And then the question is like, how the heck do you figure out what numbers are here and here?
Yeah. Well, you know when you're negative because of the final product.
You know that because the final product one is negative. You got a negative there, yep. And then what's the pattern? Yeah?
I usually do, I figure out like what is multiplied together to make 21.
Mm-hmm.
And then figure out if that adds up.
You're almost right, okay? I think you probably, it's what multiplies to minus 21. The negative matters, but that makes sense. It's the exact pattern. And then what adds to negative 4. That's what the numbers you're looking for. So those two numbers, they have to, and the reason is that this minus 21 came from multiplying 3 and negative 7, right? That's where it came from. And this negative 4 came from adding the two together, right? So that's your clue. So what numbers multiply to make minus 21 and add to negative 4?
I usually just list factors.
Yeah, exactly. You say like, oh, minus 21 is negative 1 and 21. Does that work? No. It's negative 3 and 7. Does that work? No, but almost, right? Mm-hmm. So what would be the correct ones?
Negative 7.
Negative 7 and 3. So x minus 7, x plus 3. And just like with the previous problem, you always can check your answer by remultiplying stuff together, right? Okay. So this one's going to be x and x. And you think what multiplies to 4 and what adds to negative 5. So if two numbers multiply to make a positive but add to a negative, they're both negative. And 4 is negative 1 times negative 4. Is that the ones? That's the ones. So minus 1 minus 4. Also, just make sure you understand this pattern depends on it being x squared. When you have like 2x squared, the pattern's different, okay? All right, this one. So we'll have x and x. Will we have both positive, both negative, or one of each?
Both negative.
Both negative. Okay, they got to multiply to 12 and add to negative 8. So 12 is it negative 1 and negative 12? No. Is it negative 2 and negative 6? Yes. Personally, if you can get it right away, great. If you can't, I would suggest being somewhat systematic in your list. Does that make sense? Like start with 1 in the number, 2 in the number, if possible 3 in the number, 4 in the number. Does that make sense? So go through the list sort of systematically, otherwise you're going to forget what you've guessed already. That's what happened to me. Now, polynomials that are prime should be really, really obviously prime, okay? Not like you just can't figure it out. Like this one, we would need something that multiplied to 7 and added up to 5. Is that possible?
No.
No. Okay, so that one is prime. So the only prime ones you should see should be pretty obvious. Does that make sense? This next one, you're like, but there is no x in the middle, right? Oh, but there is. I'm going to make one. X squared plus 0x plus 4. Okay, does that make sense? So, okay, we need stuff to multiply to make positive 4 and add up to 0. So 4 is 1 times 4, right? It's 2 times 2. Why is negative 2 and positive 2, why is that not actually even an option? Because they multiply to make negative 4, not positive 4, right? So are there any things that multiply to make 4 and add to 0? No. So that one's also prime. Does that make sense? Okay, how about this one? What is the middle number with that x?
1.
1, yep. Technically negative 1, but I think you know what you mean. So we need things that multiply to make negative 1 and add up to negative 56.
You got that backwards.
Oh, jeez.
Yeah.
Ah! too early. Okay. Multiply to negative 56 and add to negative 1. I'll say it louder. Negative 8 and 7. Yeah. Well, the point is the negative has to be on the right one. Yep, exactly. So this will be x minus 8, x plus 7. And that's the most common kind of factoring you're going to see. We'll do some of the harder ones on Tuesday because you have Monday off. So, since I failed to record this during class, let me do it now. So when your leading coefficient is something different than just x squared, when you have like 2x squared, the guessing and checking doesn't have as easy of a pattern. So here's how you guess and check, and after I show you this, I'll show you another way called grouping. So this came from, hopefully, from 2 linear factors, and to make 2x squared, one of those had to be 2x, and one of them had to be x, as taking this 2x times that x is what makes the 2x squared. So then you have a couple options. These last numbers that go there and there, they have to multiply to make negative 2. So either you have 2x minus 2 and x plus 1, or you could have something like 2x minus 1, x plus 2, and of course the signs could flip-flop. So let's check and see if those are right by multiplying. So for this first one, I'll just do the checking in a different color. We'd get 2x squared plus 2x minus 2x minus 2. And the first term checks out and the last term checks out, but the middle two terms cancel and don't give us 3x. So this is not the correct answer. This one, we get 2x squared plus 4x minus 1x minus 2. And that does check out. So this is, as one student said rather well today in class, easy to do if your first number is prime. Now an alternative way is called grouping, and this grouping way is sort of a hybrid of the other method that we used, and a couple earlier examples where we did actually use grouping to factor. So step 1 is to multiply what I would call A and C, the number in front of the x squared and this number on the end. So multiply 2 and negative 2, which is equal to negative 4. Then you need to find numbers that multiply to negative 4 and add to 3. And the numbers that satisfy that property are 4 and negative 1. Now here's how you use them. You take your original polynomial, and you unadd the middle term like so, using those two numbers you just found, 2x squared plus 4x minus 1x minus 2. And you should be able to check and see if you're at least somewhat correct by checking that 4x minus 1x does indeed equal 3x. What you're doing here is you are uncombining the common terms that you combine to simplify your answer. Now look at the terms in two groups and take out the greatest common factor from each group. And that first group is 2x. And the second group is negative 1. Notice that becomes plus when the negative gets factored out. And that factors into x plus 2 times 2x minus 1. And notice that even though the terms are in the opposite order, that's the same thing as example A. And this method is better when your leading coefficient, the thing with the x squared, is not prime. So for example, with this one, if we're doing that grouping method, we multiply 6 times negative 4, which is minus 24. And the negative matters, so be careful. We numbers that multiply to minus 24 and add to 5. And the numbers that satisfy that property are 8 and negative 3. Notice that if those numbers are going to multiply to make a negative, one has to be positive and one has to be negative. So this factors into, or expands into 6x squared. I'm going to put the negative 3x first and then the plus 8x second. And I'll look at them in groups of 2 and take out the greatest common factor from each group. So I have 3x times 2x minus 1 plus 4 times 2x minus 1. And you'll know that you're right when you get these matching linear factors. Here we have matching 2x minus 1s. And your final answer is 2x minus 1 times 3x plus 4. And it does not matter which order those terms are listed in. And if you're uncertain if you're right, you could just multiply them together to check. Now this next one's a little bit different because it has x and y in it, but in general, same principle applies. Just multiply that 2 and negative 4. So we need numbers that multiply to negative 8 and add to 7. And the numbers that satisfy that are 8 and negative 1. So that is the same thing as 2x squared plus 8xy minus 1xy minus 4y squared. So the only difference there is that your middle term is not just x, it's xy. Now in your first pair of terms, your GCF is 2x. We're left with x plus 4y. In the next set of terms, your GCF is negative 1. Oh, a negative 1y, excuse me, x plus 4y. And final factored form is x plus 4y times 2x minus y. And one more. 4x squared minus 15xy minus 4y squared. So multiplying the 4 and negative 4, we need numbers that multiply to negative 4, 16, negative 4 times 4. And add up to negative 15. And the numbers that satisfy that will be negative 16 and 1. So this is 4x squared minus 16xy plus 1xy minus 4y squared. And the 16xy and the 1xy, those can go in any order. Your intermediary work will look different, but your answer should be the same. Take out your greatest common factors. We'll have 4x times x minus 4y plus y, x minus 4y. Now x minus 4y is your GCF. And you're left with 4x plus y. Now factoring is all about recognizing patterns. And one pattern is called the difference of squares pattern. So it's when you have something squared minus something else squared, that factors into a plus b times a minus b. Notice that this number is the square root of your first term, and this number is this number, there and there, they're the square root of your second term. And you have one factor that's positive and one factor that's negative. And you could verify that this is true by multiplying the polynomials on the right together. When you do so, you get a squared minus ab plus ab minus b squared. And so those negative ab, positive ab cancel, just giving you a squared minus b squared. And I can explain that one other way with this pattern x squared minus 25. Think about that as x squared plus 0x minus 25. We need two numbers that multiply to make minus 25 and add to 0. And those numbers are 5 and negative 5. So this will factor into x plus 5 times x minus 5. And you have to look and see what happened from the original problem to the answer. The x squared became x and x. And the 5 is the square root of 25. And that pattern generalizes even when you don't have just x squared. Like for example, here I have 9x squared. So that means that my a is 3x, or the square root of 9x squared. So I'll have 3x times 3x. And the square root of 4y squared is 2y. So one factor will be 3x plus 2y. One will be 3x minus 2y. And similar idea here in the last one. This will factor into x minus, sorry, we'll do plus first, x plus 4y, x minus 4y. So the hint that you have to use those factor patterns is that you see two terms. So two terms, two terms, two terms, and they both are square rootable. Technically, in this lesson, we're doing what's called factoring over the integers, meaning that our numbers here are actually just whole numbers. Technically, this applies to stuff like x squared minus 5. That technically factors over the real numbers into x plus root 5, x minus root 5. You won't have to do anything like that in this class yet, but eventually we'll go there. Now another pattern that is pretty tricky, so there's two of them, it's called the sum and difference of cubes pattern. So this says if you have something cubed plus something cubed, it factors into the cube root of that first something plus cube root of that second something, that's the a and b, into a squared minus ab plus b squared. It's really, really easy to show this is true, just distribute. So like first distribute a, and you'll have a cubed minus a squared b plus a b squared. Then distribute the b, we'll have plus a squared b minus a b squared plus b cubed. And you can see that this a squared b cancels with that a squared b, and this ab squared cancels with that negative ab squared, just giving you a cubed plus b cubed. And the same thing is true, you can prove a cubed minus b cubed quite easily. Now a couple things to note about how you choose a and b. So when you pick a and b, a is equal to cube root of the first term, b is equal to cube root of the second term. If you have a formula that is a cubed plus b cubed, use the first one. If it's a cubed minus b cubed, use the second one. Your values of a and b will always be positive. The plus or minus sign between them just tells you which formula to use. So let's do an example. So here we have z cubed minus 27. So a will equal z, and b will equal 3. Notice 3 is the cube root of 27, and z is the cube root of z cubed. And this will factor into a minus b, a squared plus ab plus b squared. So that's z minus 3 times z squared plus 3z plus 9. And this second polynomial will almost always be prime. It should be quite easy to tell. You would need numbers that multiplied to make 9 and added to 3. And the only numbers that multiply to 9 are 1 and 9, which adds to 10, and 3 and 3, which adds to 6. So that second polynomial does not factor anymore. And I believe the only instance in which it will be if you have a greatest common factor of some sorts, but I'm not 100% certain of that. Now for this next one, we're going to use the plus formula. So that is a plus b, a squared minus ab plus b squared. And a is the cube root of 8m cubed. So a is 2m, and b is the cube root of 1, which is just 1. So this will factor into 2m plus 1 times. Now 2m squared is 2m times 2m, which is actually 4m squared, minus 2m plus 1. And lastly, let's solve a problem that is sort of more calculus-like. So you might solve a problem like this in calculus class at some point in time in your life. A rectangular open-top box is to be constructed out of 9 by 16-inch sheets of thin cardboard by cutting out x-inch squares out of each corner and bending the sides up. Express each of the following quantities as a polynomial in both factored and expanded form. So first we want to find the area of the box after removing the corners. So we have a box, or a piece of cardboard. It is 16 inches, we'll say long, and 9 inches wide. And we're going to take that box and we're going to cut it. We're going to cut out little corners. And then we're going to fold and tape the box into a boxy shape. So those dotted lines now constitute the base. And this thing outlined in blue is the cardboard that you're actually going to use for the box. The rest of it is just waste cardboard. So the sides you cut out are all x. And to find the area of the cardboard, you'll find the total area of the sheet, which is 9 times 16 minus, you've taken out 4 corners and each has area x squared. So minus 4x squared. So that's the same thing as 144 minus 4x squared. So that is the expanded form. In factored form, we've got to take out the greatest common factor, which is 4. And that's the same thing as 4 times 9. Whoopsies, that should be 6. So 4 times 6 minus x and 6 plus x. So that's factored form. And each method is useful for its own thing. So for now, what you're supposed to do is just practice finding each of them. Next, we're asked to find the volume of the same box after it's folded up. So same picture. You cut out these corners. Now the volume of a box is length, width, height. Assuming we fold this box up, the height is going to be x, and the length is the length of this side, from this edge to that edge. And if that whole thing was 16, and you cut out 2 x's, the length is 16 minus 2x. And similarly, the height, or actually the width, the width will be 9 minus 2x. So your volume is x times 16 minus 2x times 9 minus 2x. And that's almost factored form. And I say almost because technically the 16 minus 2x has a GCF of 2. So take out that 2. And we'll have 2x times 8 minus x, 9 minus 2x. So that's your volume in factored form. In expanded form, I'm going to multiply the 8 minus x and the 9 minus 2x first. That is 72 minus 16x minus 9x plus 2x squared, or 2x times 72 minus 25x plus 2x squared, or 144x minus 50x squared plus 4x cubed. So that's the volume in expanded form. So those formulas allow you to plug in any x that tells you sort of how much you've cut out and figure out what the volume would be. Now, first of all, notice that your x's have to be between 0 and 8. Because if you cut a thing of 0, you have no box. You've cut no sides, so you still have a rectangle. And if you cut out 8 from each side, you have effectively cut the box into 4 pieces, and this is no longer a box. So 0 to 8, not including the endpoints. If you go out of that range, you're going to get boxes that have weird things like negative area. So the physical situation means that x must be between those numbers.